The second we flush, it's all over for most of us. For others, the process of treating wastewater has simply just begun. If you've ever wondered where it goes, but more importantly, where it ends up, we will attempt to answer that question by taking you through the entire process, flush to finish. Every home and business uses water and generates wastewater. Once waste is flushed down a toilet, it travels down a lateral into a main pipe where gravity begins the process of the flow toward the wastewater treatment plant. The wastewater travels through miles of pipe before eventually arriving at the plant. The city's wastewater plant treats wastewater from residential, industrial, and commercial customers throughout the city. The plant cleans the sewage and eventually discharges to a ditch, which eventually drains to the Wood River. The water is treated to standards set by the DEQ and in many respects is very close to a drinking water standard. As a part of the permitting process, the facility samples all of the wastewater entering and leaving the plant. Portable refrigerated samplers are on site to meet that standard. Not only do they sample the raw wastewater coming in from the community, they also sample the JBS flow as well. When gravity is doing the work of carrying sewage, it's considered a free service. In an ideal scenario, gravity carries the sewage from the home all the way to the treatment plant. Because of the nature of our flat terrain, the gravity sewer mains eventually become too deep for practicality, and the wastewater must then be lifted by means of a pump at what is called a lift station. The term lift station comes from the process of using a pump to lift the sewage up in elevation to allow gravity to once again begin its work of delivering the sewage to the treatment plant. As wastewater enters the treatment plant, it flows through a bar screen to screen out large solids. It's amazing what can come through the wastewater collection system. Plant staff has reported over the years finding numerous diapers, 2x4s, bricks, underwear, toys, and even false teeth, which the owner did in fact want returned. A mechanical rake system is used to keep the bar screen clean. This chain, which operates the rake mechanism, helps filter out the trash, separating it away from the wastewater. The rake dumps the solids into a bin inside the station, manually cleaned out, and is later hauled to the landfill. Take a look at the bottom of this rake mechanism. Over 45 years of wear and tear has caused the bottom supports to rust through. Staff had to re-engineer and fabricate a piece of 1.5-inch channel iron to replace the existing support to keep the mechanism operational. Purchasing replacement parts for this equipment is not an option, it's too outdated. Examples like this show just how valuable it is to have a skilled staff in place to address a variety of fabrication challenges. Part of the wastewater treatment plant's capital improvement plan is a project to construct a new bar screen and rake mechanism. Rather than manually having to clean the mechanism as they do today, an upgrade would automatically shred, compact, and wash the waste, drying it into a very fine material which would then be hauled to the landfill. Over the next 2 years, the facility is aiming to become a cleaner operation by installing a much finer screen into this part of the process, which in turn will filter out more waste and reduce wear and tear on the pumps at the plant. Wastewater continues through the bar screen and into the wet well, where grease balls begin to form. Simply put, grease that is dumped down the drains and empties into the sewer system will form a ball around any solid waste item in which it comes into contact. An example would be grease forming around a cigarette butt or dish rag. As it forms, these grease balls can become larger and larger and eventually have to be cleaned, which requires staff to collect the grease balls every few weeks. If they are allowed to get too big, they have been known to plug pumps and cause a variety of damage. You can never tell by looking here, but wastewater is actually 99.8% water and less than 0.2% solid material. Once the wastewater enters the facility, we dive a little deeper, if you will, into the pump station wet well. We are now down 15 feet below grade or below the ground. The sewer which brings all the wastewater in is closer to 25 feet below grade or below the ground, which means there is 10 feet of raw sewage under our feet at this point, 5 feet of open air, and another 10 feet of raw sewage. The pumps on the other side of this wall pick up the sewage and take it to what is known as the headworks part of the facility. There are 18 sewage pumps which pump raw sewage out of the city and into the wastewater treatment plant. The raw wastewater pumping station at the plant is the largest lift station in the city of Grand Island. It consists of 5 main pumps with a capacity to pump up to 40 million gallons of wastewater a day. The ability to continue to pump wastewater every day is critical. That's why this main pump station has 2 sources of backup power in the event of something going wrong. The 18 lift stations throughout the community are also designed with backup power sources. This design and redundancy is to prevent sewage backup in our basements. In a worst-case scenario, a complete system failure of this lift station would be detrimental to the city of Grand Island. Although there is some capacity in the collection system, the inconsistent slope of the terrain and the different areas of town would cause some basements to back up in a matter of minutes and others in 2 or 3 days. For this reason, the level of redundancy is spread throughout the plant to ensure the community can continue to operate. This pump station was built with the original plant in 1965. Through maintenance and ingenuity of plant staff, they have found a way to keep the equipment operational for almost half a century. Without exceptional fabricating ability and annual maintenance, this equipment would have been replaced some 20 years ago. Something else of note, in 2008, over 50% of the plant's inflow was from infiltration and inflow, or I&I. Infiltration is groundwater finding its way into the collection system through every crack, crevice, or leaky pipe it can find. Inflow is rain finding its way into the collection system, or a basement dewatering sump which is discharging into the system. In 2008, during a period of heavy rain and flooding, the plant registered a peak flow of 38.5 million gallons per day for a span of 15 to 20 minutes before it leveled off at 35 million gallons per day. The peak instantaneous flow design for the facility is 40 million gallons per day, so it's easy to see how quickly I&I can affect a plant at a moment's notice, taking it to capacity. This 16-inch pipe stretching horizontally across the wet well is the JBS sewage flow. This meatpacking plant has a flow that comes in separately from the rest of the community. In a town close to a population of 50,000 people, this meatpacking plant is the largest single customer, discharging up to 4 million gallons of sewage per day. In the late summer months of 2010, the city's wastewater facility was averaging 12 million gallons a day, with 3.5 million gallons of that flow belonging to JBS. Not only are they a large percentage of the daily flow, but have been known to contribute over 50% of loading on some days, thus requiring a separate flow. This is the upper level of the dry well side of the raw wastewater pump station. It contains all of the electrical equipment and the motors to drive the pumps down below. There are 5 main pumps, 3 of which are driven electrically, the 4th can be driven with a diesel engine, and the 5th can be either electric or diesel. Again, the diesel and electric redundancy options are built in to keep the wastewater moving through the facility. There is a 100 kilowatt diesel engine generator located outside, which can provide electricity to power the entire pump station if needed, along with the capability of using 2 of the plant's main pumps operating on diesel power. The first 2 pumps on the left can move from 5 to 7 million gallons per day of wastewater. The far 3 pumps can move anywhere from 8 to 14 million gallons per day. The system is designed to maintain a constant level in the wet well by use of a bubbler control system. The bubbler measures the depth of the wet well and in turn adjusts the speed of the pumps accordingly, pumping sewage to the headworks of the plant. Once the wastewater leaves the pump station, it travels here to what is known as the Parshal flume, named after a French scientist who was instrumental in its development. This attachment protruding from the concrete may not look important, but it might save your life. JBS uses an anaerobic environment for the pre-treatment of their wastewater. As a result, they convert a lot of their sulfate in the water to sulfides. When JBS combines with the rest of the community's wastewater, it can make hydrogen sulfide, which has a very strong scent similar to that of rotten eggs. This situation becomes dangerous when high concentrations of this gas exceed 200 parts per million or milligrams per liter and can cause paralysis to your breathing system. This meter is constantly taking measurements of the air and reporting back to a digital readout with a constant log. In addition to keeping staff informed as to a potentially life-threatening situation, it also alerts staff to hydrogen sulfide levels that can be considered offensive in the community. At that point, corrective action can be taken. The Parshall flume measures the wastewater and then splits it into two parallel flows to one of two grit basins to remove sand, gravel, and other gritty material. Each grit chamber is 10 foot wide, 12 foot long, and 15 foot deep. The basins are sloped toward the center so all the heavy materials move to the center, settle, and are removed. This facility will pull out up to 2 cubic yards of grit per week, almost enough to fill a normal-sized pickup. Heavy rain events can double the grit because of I&I. Next in the process, wastewater moves to the primary clarifiers. The primary clarifiers are speeding up the process of Mother Nature by allowing solids to settle out. If raw sewage was dumped into the environment, be it in a lake or river, the first part of the process that would take place is the settling out of solids, exactly what we see happening here with the primary clarifiers. The primary clarifiers are a 75-foot diameter tank with a sloping bottom where primary settling occurs. The outside depth of the tank is 7.5 feet, while the center depth of the tank is 10.5 feet. To promote settling, the flow of wastewater is slowed through the tank, taking from 60 to 90 minutes to flow through. The primary clarifier mechanisms were replaced in 2010. The skimmers you see going around the tanks are only a very small part of that mechanism. Down below is a very large steel framework that moves around the tank. At the bottom of the mechanisms are scrapers that work with the slope bottom and move the solids to the center of the tank for removal. The solids are pumped off using a progressive cavity pump to a holding tank where they are kept fresh by adding air. The water that comes off the primary clarifiers has 25 to 50% of the suspended solids removed. So we began the process with the flush. It carried through the city mains, across the bar screens, through the wet well, into the main pumps, past the grit basins, and out of the primary clarifiers. We have now completed the primary treatment process and are now ready to move on to the secondary treatment process. An interesting side note, on a typical day the facility will remove 10 to 15 tons of suspended solids and BOD. Biochemical oxygen demand, or BODs, is a method used in the scientific community to measure the biological strength of the wastewater to use up or demand oxygen. That method is also used here at the plant. The Grand Island Wastewater Treatment Plant makes a concentrated effort not to use any artificial chemicals or treatments throughout this process. They are simply growing the bacteria, or bugs as they call them, found in nature. The bugs begin to eat the raw waste in the water. By growing these bugs in a controlled environment, they accelerate the speed of a process very similar to what Mother Nature uses to clean water. This type of treatment, using bacteria, has been used in the United States since the late 1800s. The first wastewater treatment plant in Grand Island was constructed in the early 1920s, where the Brudick Power Station now resides along Cherry Street. Construction started in 1965 and was completed in 1967, with major additions made in 78 and 95. Over time, the equipment may change, but the process has always remained much the same. This is at the beginning of the aeration basin where the primary effluent, or water going out of the primary clarifiers, is mixed with the bugs or bacteria found in nature that we referenced earlier. The water is pumped through this station and moved up into the aeration basin. There are 3 screw pumps involved in this process that measure 7 feet in diameter, 35 feet long, and are capable of pumping 17,000 gallons a minute. If you have a 3-foot deep and 20-foot diameter pool in your backyard, these pumps could empty it in less than 25 seconds. Much like the lift station we saw earlier, this pump station is equipped with its own 100 kilowatt generator in the event of a power outage. The reason these pumps move so much water is that up to 400% of the flow is recycled for nitrogen removal. What we are looking at now is the aeration basin complex where the biological treatment part of the process takes place. Each basin is approximately 260 feet long, 66 feet wide, and 16 to 20 feet deep. Each basin has a capacity of 2.7 million gallons of water. The Scumplex, as it's known, was built in 1994. It has 15,000 cubic yards of concrete in it and enough steel to construct 4 double-lane bridges across the interstate. The aeration basin contains all of the bacteria and biota used to treat the wastewater and remove suspended solids and biochemical oxygen demand, or BOD. The removal of nitrogen or ammonia from the wastewater is a requirement based on the discharge permit currently in place at the plant to protect drinking water and fish habitat. This particular aeration basin is capable of meeting that standard. The 4 blowers inside of this building are 700 horsepower, each capable of putting out 10,000 cubic feet per minute of air, enough air to empty a 1,200 square foot house in 58 seconds. Typically, no more than 2 of these blowers are running at one time. The green piping you see stretching horizontally is low pressure air piping. Each basin receives 5,000 to 7,000 cubic feet of air per minute to help support the biological life. The air that is piped through this system is generally a warm air, allowing the bugs to live and grow and break down the ammonia into nitrates. The warm air also keeps the water from dropping below 55 degrees, keeping the process of Mother Nature moving at an accelerated pace. Each basin contains approximately 2,500 ceramic diffusers to break up the air into little tiny bubbles so that the biological life can use the oxygen. The first part of each aeration basin is 700,000 gallons and operates as an anoxic zone or without oxygen. The second part of each basin is 2 million gallons and is aerated or oxic, meaning with oxygen. Once ammonia nitrogen hits the aerated part of the basin, it converts into nitrates by uptake with the oxygen. This is when the 400% recycling begins its process, this time landing in the anoxic zone, allowing the bugs to take the oxygen molecule off of the nitrates, leaving nitrogen gas behind. So in general, we nitrify in the anoxic zone and denitrify in the oxic zone. What we are looking at now is the bacterial flock as it mixes in the anoxic zone. It's attempting to coagulate or stick together. Without the giant mixers that are in these basins, the water would turn clear on top and all of the solids would settle to the bottom. This would not allow the bugs to make contact with the nitrates, thus not uptaking the oxygen off the nitrate molecule, and the nitrify and denitrify action wouldn't happen. While we have said that we are accelerating the process of Mother Nature, it's interesting to note that through the recycling process, solids remain in the system up to 16 days. There are several hundred tons of solids within this system, with only 2 to 3 tons being removed each day. Without the solids containing the bugs, there would be no way to treat the waste. It's ironic that removing the solids is the focus treatment in the beginning, only to be added back into the treatment process later to further treat the water by supplying food for the bugs. Who would have thought that removing the solids from the water is as vital as adding them back in? Once the water leaves the aeration basins, it goes back to clarifier basins, but this time they are final clarifiers. A fence surrounds each of the 3 clarifiers to prevent excessive wind loading on the surface. On a windy day, scum buildup will get pushed to one side and go over the edge, releasing solids with the final effluent, or water going out of the plant. The final clarifiers act very much in the same way as the primary clarifiers, with the only real difference being the depth. The deeper clarifiers allow more solids to settle out. These upright pumps are what move the solids from the final clarifiers back out to the aeration basins for recycling. Each one is capable of pumping 3 million gallons per day. The smaller pumps on the left are used to waste the solids out of the bottom of the clarifier and back to the waste sludge holding tanks we referred to earlier. Each of these recirculatory pumps has a price tag of over $20,000 apiece. According to the NDEQ, or Nebraska Department of Environmental Quality, the Wood River is classified as a warm water B stream, which means the effluent must meet warm water B stream standards for fecal coliform and E. coli. A UV disinfection facility disinfects the water as a part of the treatment process. UV is considered to be a very safe and efficient means of wastewater disinfection. Inside of the UV disinfection facility, we elevated a bank of UV lamps to help illustrate not only what is being used in this part of the process, but how they work day to day. The small circular white rings that are moving back and forth are actually cleaning the lamps. Each ring contains a scraper to clean the bulb. The center of the ring contains a lime-away gel to remove hard water stains off of the bulbs. The cleaning mechanism is powered by the hydraulic system seen here. The fluid used within this system is a food grade, which means if a leak were to occur, the employees and the environment are not harmed. There is quality control sampling and testing performed throughout the plant, but here at the final sampler is the most important sampling that is performed. This sampler takes a portion of the plant effluent, or water going out, with 2 to 4 samples every hour. Facility staff also test every day for BOD, suspended solids, nitrogen, and E. coli. Test results determine whether or not the plant is protecting the environment and meeting the permit requirements. This facility supports 240 feet of finger weir within the UV disinfection system. Under the grate, you can see the small channels that are a part of that system. A weir is an engineered system used to maintain a constant flow of water. It's in place to ensure that the flow of water being treated is not coming through the system too fast. In other words, every drop of water is receiving the same amount of exposure to the disinfection system to ensure permit requirements are being met. The flow that exits the UV disinfection system here on the northeast side of the building travels down through this junction box and out through this discharge, which contains again a partial flume. It continues down another junction box and out a 42-inch pipe into the storm sewer outfall ditch that is north of Swift Road. After all the treatment, this is what is left behind. At this point, the water is less than 10 milligrams per liter suspended solids and BOD. Ammonia in the effluent is generally less than 1/2 per part per million, which is much lower than what the facility permit allows. A mile east of the facility, the flow enters the Wood River. This completes the liquid portion of the treatment process. We still have to review the solids portion of the treatment process. The primary and secondary solids are moved to these 2 holding tanks, where they are stored and aerated before dewatering and later hauled to the landfill. The sludge runs through the belt filter press. The top, or yellow section, is the gravity belt thickener, where water drains out through gravity. The lower section, where the yellow and orange belts meet, is where the water is pressed out of the sludge. The dewatered sludge cake drops off the press to an auger that carries it to a truck. It's important to dewater the solids in order to keep the weight down of every load being taken to the landfill. This ultimately translates to money saved. By removing as much water from these loads as possible, it keeps the weight of the load down and in turn keeps costs down. It's common practice for only one of these two tanks to be in service on any given day. The second tank is now used primarily as a backup. Of course, the process is much more technical in ways that we can't even begin to describe, but what's important to remember: we should never take our water for granted, or the men and women who work so very hard to protect and treat it.